Okay, in this video we're going to look at a few more examples of solving differential equations using the Laplace transform method. Okay, so as usual we're confronted with a differential equation, and what we're going to do is we're going to translate this differential equation into an algebra equation. Now just of course all the time we've got these tables are at the back of your manual, and the relevant transforms here is that a first derivative f dashed of t gets transformed to s times big F of s minus little f of 0. And a second derivative f double dashed of t gets transformed to s squared times big F of s minus s times little f of 0 minus f dashed of 0. So these are the relevant things here. And of course, little y of t transforms to big Y of s, and 0 as a constant gets transformed to, well, I should probably have written down here a constant a gets transformed to a divided by s. Okay, so we'll take the Laplace transform both sides. Now there's something here that we need to be a little bit careful of, and that's basically using brackets. So I'll show you what I mean. So we'll send the second derivative here using this Laplace transform. Now here the role of f is being played by y. So instead of big F we've big Y. Instead of little f we've little y. Instead of little f here we've little y. We'll come over here. So s squared, not big F of s but big Y of s, minus s times little f of 0, little y of 0, minus y dashed of 0. Okay, the Laplace transform is linear, which means we can fix the constant 4. And what I'm writing in the next few seconds is not quite correct, but we'll fix it. So the y dash of t gets sent to s times big F of s minus, not f, y, minus little y of 0. Now as written this is not quite correct because of BOMDAS. The 4 multiplies this, but really it should be multiplying both of them. So you have to be careful that you include this bracket because the 4 also multiplies this. That's the thing you need to look out for. So that's that, plus fix the 4 here, and then little y of t is sent to big Y of s, and then a constant 0 is sent to 0 over s. Now you can say there's something, for any linear map 0 will be sent to 0, but I think you're better off doing 0 divided by s, because if there's a 1 here it doesn't get sent to 1, it gets sent to 1 over s. So I think it's a good habit, certainly for a while, to put 0 divided by s, because you are taking the Laplace transform on both sides. This kind of emphasizes that you're doing that. Okay, so now we want to apply our initial conditions, and they'll be given in the question that y of 0 is equal to 1 and y dashed of 0 is equal to 0. So let's do that. So if s squared times big Y of s minus s times y of 0 minus s times 1 minus, I might just put it in red just to emphasize, minus y dashed of 0 is, oh dear, having a mare here, this is 1. Y of 0 is 1. It's 1 here. Minus y dashed of 0 is 0. Plus 4 times s times big Y of s minus little y of 0, which is 1. Okay, and plus 4 y of s. And now this is the, a lot of people, or a lot of students sometimes, I'm not great at writing these. This looks like 1 over s. It's not, it's big Y of s. That's a y there. So maybe you might want to start putting tails on them. I won't be doing that. And then this is probably the point to say that 0 divided by s is equal to 0. Okay, so now our job is to solve for big Y of s. Now what I'm going to do here is I'm going to just multiply this bit out. The writing is probably going to have to go small here, and I might have to skip a step, we'll see. So I have s squared times big Y of s minus s times 1 is minus s, minus 0 doesn't do anything, 4 times s times y of s, and then this is the bit that without the brackets you'd mess this up, you just have minus 1. It's 4 by minus 1, which is minus 4, and then plus 4 times y of s equal to 0. Now if you're trying to solve this for y of s, what you have to do is get all the y of s's on one side as such, get rid of this, and get rid of this by adding s and adding 4, in other words adding s plus 4 to both sides. And I will skip a little line here because I don't seem to have the space. I'm just going to make a note for myself for next year. Space, need more space here. So we're going to add s plus 4 to both sides to get rid of that and that, and at the same time I'm going to take the common factor y of s out of this, this, and this. Yeah. So if I take out the common factor of y of s, I've got s squared plus 4s plus 4 equal to, and I'm adding the s plus 4 to both sides, so that's gone when I add the s, that's gone when I add the 4, and 0 plus s plus 4 is s plus 4. And all that remains to do to solve for big Y of s, this is, we'll do big picture in a second, is divide both sides by s squared plus 4s plus 4. And this is, as we said, this is what we were doing earlier. We were starting on at this point and then finding the inverse Laplace transform, but that's after doing this. So this is the bit where you've turned the difficult problem, a differential equation, into a very easy problem, which is an algebra equation, and it's very easy to solve that algebra equation. But now becomes the medium difficulty bit. You have to send this back. Now what you should do at this stage is have a little look in the tables, and now maybe I should probably have tables with me all the time, but I don't. It'd be great if I did. If you look in the tables, there's nothing quite like this. There's nothing with an s, there's s squared plus 4, but nothing with a 4s. So the suggestion is this is maybe things multiplied together. So what you have to do with this is write it again as a sum of simple things. And writing this thing is called a rational function, sums of powers of s divided by sums of powers of s. Writing this as a sum of simple things is called partial fractions. So this is what we need to do here. The first step with partial fractions is to factorize the denominator, or the bottom. So I need to factorize s squared plus 4s plus 4. So we've got s squared plus 4s plus 4. And I'll use this AC method. I'm going to do a by c. 1 by 4 is 4. Look at all the factors of 4. Which are 1 by 4, 2 by 2, 3 doesn't go, 4 I already have. And can I make a plus 4s? Yes, I can, with plus 2 plus 2. So I can rewrite this middle term as s squared plus the 4s is equal to 2s plus 2s. And if you do that, you can factorize it, because you can take out something common out of the first two, which is s. That leaves s plus 2. And then something out of the second two that leaves s plus 2 again, that would be 2. And then you've got a common factor between these two of s plus 2. So it's s plus 2 times s plus 2. Now what would be tempting, excuse me, what would be tempting at this stage is to say, okay, what are my rules? Oh, I've got a rule 1 here, and I've got another rule 1 here. But unfortunately, these are the same. So it's not a rule 1. If you've got two things of the same, it's a rule 2. Okay, that means that you can't use the cover-up method, so things are going to be a little bit trickier. Okay, so what do? Well, take your Laplace transform this and write it with the bottom factorized, perhaps as s plus 2 all squared, as this is. So you have y of s is equal to s plus 4 divided by s plus 2 squared. Now there is a clever thing you can do here. There is a shortcut to this. If you find it, that's great. Otherwise, I recommend doing it this way. Okay, so rule 1 says, rule 1 says that you'd have a constant over s plus 2 plus a constant over s plus 2, but because it's a rule 2, this isn't basically not going to work. So rule 2 says you need to change the second one by squaring this. Now, unfortunately, I won't say like why is that the case. This is a case where I would say it is a rule, and what I mean by that is it's basically a theorem. If you go into the theorem, you can see why it always works, but that's not quite our concern. And our job now is to find constants a and b such that these two are equal for all values of s. So what I say now is I want this to equal this. So the best way to compare these things is to write the right hand side here as a single fraction with the bottom the same. So what that means is I want to write this as a single fraction with a common denominator of s plus 2 squared. So my recommendation is, okay, this is over s plus 2 squared, that's fine. Do something with the first term here. So what I recommend is, now you have to be careful, you can't do whatever you want. Like, so one suggestion would be, okay, if you square above and below, but it won't be the same thing. Like, for example, if you have a half and you square above and below, you get a quarter, and a half is not equal to a quarter. You can't just change things. So you have to be a little bit more careful than that. What you have to do is, okay, sure, you want to multiply the bottom by s plus 2 to turn it into s plus 2 squared. That's fine, but this changes it. How do you balance the books? And how you do it is you multiply the top by s plus 2. Now, doing the same thing above and below, for example, squaring doesn't necessarily give you the same thing as you had before. So, like say, adding 1 above and below would tell you that a half is equal to 2/3, but that's not actually true. But multiplying above and below and similarly dividing above and below is fine, because what you're actually doing is you're just multiplying by 1. And now you still have plus b over s plus 2 squared. And now you've got a common denominator, s plus 2 squared. They look different, but that's also s plus 2 squared. So you have equals a times s plus 2 plus b divided by s plus 2 squared. Right, you want this to equal this. This is equal to this. This is equal to this. So you want these two to be equal. What do they have in common? The bottoms are the same. So what you need to do is you have to say, okay, if I want these to be equal for all values of s, I need those tops. So what's the fancy word being numerator? You need these numerators to be equal. So we're going to force this to equal this. We'll do that on the next page. So compare the numerators. Well, you say compare, we'll force them to be equal. If you're kind of chancing your arm and making up your own partial fraction rules, you'd be comparing the numerators. But here the theory says you can definitely do this. There are values of a and b that make these equal for all values of s. So I would say force is probably a better word. But anyway, s plus 4 to be equal to a times s plus 2 plus b. Now what you're fully entitled to do is to compare the coefficients of s on both sides. This would tell you quite quickly that a must be 1, and that would tell you shortly afterwards that b, I think, must be 2 as well. And this is fine. This would be kind of a chapter 2 technique, or also the technique that of doing the complete the square. But in these notes I've persisted with putting in values of s. So things are equal for all values of s. You can sub in whatever values of s you want. Now the clever value to put in here for s is -2, because this will kill this and you will know what b is pretty much immediately. So I'm going to substitute into both sides s equal to -2, and I get -2 plus 4 is equal to a times 0, that's just 0, plus b. And immediately you have that b is equal to 2. That's good. The next thing that we should do is substitute into both sides s equal to -1. Okay, why minus 1? Well, there's actually no good reason. Well, I have a good reason. You could actually put in whatever value of s you want. You could put in 63. It doesn't really matter. 0 is usually a nice value to put in because it'll make this 0 and this 0. I've chosen minus 1 on this occasion because minus 1 plus 2 gives me 1. I'll have a by 1, which is nice. So that's why I'm choosing minus 1, but actually any value of s will do. So if you're not sure, just bang in something. I think 0, 1, these are all kind of easy values to put in. So minus 1 here, plus 4 equals a, which is certainly what we're looking for, times minus 1 plus 2 gives us 1. That's why we chose minus 1, plus b, but you have to recognize that you already know b is equal to 2. So here what you can do is you've got a, well, we've got 3 is equal to a plus 2. Maybe we've got space to tidy this up. 3 is equal to a plus 2. Take away 2 from both sides, you end up with a is equal to 1. So going back on what you had, the original was, we knew that the big Y of s, the thing we were hoping to send back, was equal to a over s plus 2 plus b over s plus 2 all squared. And we know that we just found that the a, I think was 1 and the b is 2, so this is where we are. Okay, now we need to send these back, and we need to send them back linearly. Now there's a little bit of explaining here. What I might do is I might just write down the answer, because eventually you will get to this stage, but I'll write down the answer and then we'll explain a little more what's going on. Okay, so we've got the y of s. Now we need to transform back to y of t. Now the 1 over s plus 2 is no problem. That's in the tables. That's e to the minus 2t. And now we do the Laplace transform linearly, and what that means is the 2 can be fixed. And I'm going to go very quickly here. So this is a 1 over s squared. Okay, and here is the formula for what you do with a 1 over s squared. So let's apply the formula. 1 over, okay, so this thing is, we'll write it up here. This is a shifted 2 over s squared. It's shifted because instead of s, I've got s plus 2. So the first shift theorem, which is down here, well, this isn't exactly the first shift theorem. The first shift theorem, let's write it. Plenty of space down the bottom, let's write it. It says that if you've got f of s plus a, so this is a Laplace transform, but instead of s in the form you got s plus a. The way you bring it back is you bring it back as normal. That's what I'm about to do. And then you multiply by an exponential shift, which is e to the minus at. And this is in the tables. Now it's a bit difficult to use, there's no two ways about it, but it is in the tables. Right, so this thing up here is a shifted 2 over s squared. So to send it back, I just bring it back as normal. And what does 2 over s squared, or excuse me, well, I fixed the 2, so that's no problem. So what does 1 over s squared go back to using this formula? T to the 2 minus 1 over 2 minus 1 factorial. And then because it's shifted, instead of s, I've got s plus 2, I multiply by this e to the minus 2t. And then I can just tidy it up. Well, 2 minus 1 is 1, 1 factorial is 1, so this 2 divided by 1 is just 1. So the constant here, as it were, is 1. So I got e to the, excuse me, it's 2 divided by 1 is 2. E to the minus 2t plus 2. 2 minus 1 is 1, t to the 1 is just t, times e to the minus 2t. And because both the exponentials have the same speed, this is critically damped. Yeah, we don't really have to talk about this section here, it's not too important. This is just kind of, it's written down as what we just did actually. So it says the first term is no problem. It's just 1 over s plus a goes back to e to the minus at. The second term is a shifted 2 over s squared. So now here it's saying shifted 1 over s squared or you could see this as 2 times a shifted 1 over s squared. So you can fix the 2 and then see it as a shifted 1 over s squared, same thing. 1 over s squared, according to this, is sent to t to the 1 over 1, that's just t, we found that. And then there's also the shifting. So this is saying, okay, this is like the Laplace transform of something, except the s is shifted to s plus 2. So this rule here says you bring it back as normal, but because there's a plus 2 there, you multiply by an e to the minus 2t. And the 1 over s squared, using this formula, goes back to t. So this is like fixing the 2, this is sending it back as normal, and then the exponential shift. And that's that all done.